Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome to the mission briefing on target acquisition. Our objective today is to understand the protocols that govern advanced retrieval and ranking, which forms the bedrock of modern context-aware artificial intelligence systems, often referred to as Retrieval Augmented Generation, or RAG. The mission title, Target Acquisition, signifies the critical first phase of any successful RAG operation, finding the most relevant source documents with absolute precision and speed. We are operating under the highest security clearance, as indicated by our classification as Level 7 access in this RAG operational dossier. Over the next several minutes, we will decompose the challenges of retrieval and introduce the specialized assets and fusion protocols we use to overcome these complexities. This technology, developed by NotebookLM, is designed to ensure that the intelligence we feed our large language models is not just fast, but fundamentally correct and contextually rich, leading to successful mission outcomes every time. Our success relies on combining different types of search intelligence effectively and understanding how to deal with conflicting data streams. Let us begin by examining the core intelligence dilemma we face. Our challenge starts with the fundamental intelligence dilemma, best understood through the analogy of two witnesses pursuing one target. We gather two distinct types of intelligence, each strong in different areas but critically weak in others. Our first witness is Witness A, the vibe checker, who delivers conceptual descriptions. Their report states, "He looked like a banker, gave off a very nervous energy, sort of reminded me of a young Steve Buscemi." This intelligence provides excellent context and meaning. It is strong on intent, but it is fuzzy on specific details. This is the nature of semantic search. Our second witness is Witness B, the accountant, who delivers specific details. Their report is concrete. He had a tattoo on his neck that said XB99, and he was holding a blue ledger. This provides precise keywords. The accountant is strong on specifics, but if the target had written XB99 instead of XB99, the accountant would miss it. Relying on only one witness inevitably leads to mission failure, either due to missing context or missing a precise match. Therefore, we must deploy protocols designed to process both types of intelligence simultaneously and efficiently. We begin with our first specialized operative, the ghost, who represents dense retrieval. The ghost's primary method is vector search. This asset specialty is concept and context matching. It understands the meaning behind the query, not just the words used. We refer to the ghost as the vibe checker because it assesses the underlying semantic relevance of the data. For example, if we submit the query feline pet, the ghost correctly identifies documents about cats, even though the word cat did not appear in the original query. This ability to handle nuance, synonyms, and conceptual intent makes the ghost essential for navigating complex, natural language queries where the exact keywords may not be present in the source documents. The ghost is our stealth operative, fast, fluid, and brilliant at finding targets who are hiding their identity through nuance and context. Its ability to map complex ideas in a high-dimensional space ensures we capture the spirit of the inquiry. To understand the ghost's method, we must explore its modus operandi, targeting by vector angle, which relies on the core principle of cosine similarity. When we vectorize a query and our documents, they become points and directions in a multi-dimensional space. We do not measure the straight line distance between the query and the document, as this is easily misled by document length. Instead, we measure the angle between the query vector and the document vector. This measures topical direction, not document size. A perfect match is represented by a 0-degree angle, resulting in a score of 1. Zero relation is a 90-degree angle, scoring 0. An opposite meaning would score -1. In the diagram, both document A, a short document, and document B, a long document, can achieve a perfect score of 1 if they are pointing in the same direction as the query, illustrating that size does not matter. Document C, which is on a completely different topic, is at a 90-degree angle, registering no relation. This vector-based approach ensures we prioritize conceptual alignment above all else. Despite the ghost's superior ability to capture context, it does have a significant operational vulnerability: the exact match problem. The ghost's embedding model is designed to group similar concepts together. For instance, it sees the identifier error 0x884 and error 0x992 as semantically similar, lumping them into the general category of computer errors. However, for an engineer troubleshooting a mission-critical system, these errors are completely different problems, requiring distinct solutions. The ghost's context-based approach fails here, resulting in a crucial mismatch when absolute precision is required. The underlying conceptual similarity masks the critical difference in the specific token. The conclusion is clear. When the mission requires finding a specific serial number, a highly sensitive code, or a precise identifier, the ghost's intuition, which relies on conceptual similarity, becomes a serious liability. This is where we need the specialized precision of our second operative. To compensate for the ghost's semantic blind spot, we rely on Asset Profile, the archivist who specializes in sparse retrieval. The archivist utilizes the BM25 algorithm, a classical form of keyword search. The archivist's specialty is exact match retrieval, focusing on precise tokens and identifiers. This operative is our accountant. Unlike the ghost, the archivist is literal and infallible when the intelligence is specific. In a case example, if the query is the identifier, XJ550, the archivist finds only documents containing that exact string, providing unbeatable precision. It does not attempt to understand context or synonyms. It simply executes a precise lookup based on token existence and frequency. The archivist is our indispensable forensics expert, guaranteeing that any mission demanding absolute adherence to specific identifiers will be completed successfully. By utilizing both the ghost and the archivist, we ensure coverage against both conceptual and literal search challenges. The archivist's modus operandi, using BM25, is primarily about balancing signal and noise. The BM25 scoring logic is built upon a balance of two opposing forces to determine document relevance. The first is term frequency, or TF, which is the reward. This is simple. The more a specific keyword, like galaxy, appears in a document, the higher the raw score. However, this feature is regulated by the saturation point shown on the graph, which prevents excessive keyword stuffing from unfairly inflating a score. The second and more complex factor is inverse document frequency, or IDF, which is the penalty. IDF penalizes common, ubiquitous words like the, a, or and, which appear everywhere and receive a low score because they provide little actual signal about the document's topic. Conversely, rare, significant words like microprocessor receive a high IDF score. By combining TF and IDF, BM25 ensures that a document is ranked highly only if it contains a keyword frequently, and that keyword is rare and therefore highly distinctive across the entire document corpus. This clever balance ensures that the search results prioritize truly meaningful content. Now we arrive at the central challenge that precedes successful RAG integration: the operational conflict of incompatible intelligence scales. We have successfully retrieved two separate lists of high-value targets, but their scoring scales are fundamentally different. The ghost, using cosine similarity, produces scores ranging from 0 to 1, as seen with target alpha scoring 0.92. The archivist, using the BM25 score, produces scores on an entirely different scale, where target delta might score 15.8 and target alpha scores 12.5. Notice that target alpha appears on both lists. The problem is that we cannot simply add these scores. Attempting to calculate 0.85 plus 12.5 is mathematically meaningless because the scores represent different metrics on different scales. It is precisely like trying to add degrees Fahrenheit to kilometers. If we cannot synthesize this data, we cannot produce a single, reliable ranking of targets. A new protocol is urgently required to normalize and synthesize this data into a single, comprehensive decision list. The solution to the scale conflict is the Fusion protocol, Reciprocal Rank Fusion, or RRF. The first mandate of RRF is to stop looking at the raw scores. The score of 0.85 or the score of 15.8 must be discarded as non-standardized data. The second mandate is to start looking exclusively at the position, or rank, in each agent's list. The inherent logic behind RRF is profound. It fundamentally does not matter why a document was ranked highly by a specialized agent, only that it was. The rank, defined as the document's position in the agent's list, is a universal, standardized unit of relevance. By focusing solely on rank, RRF provides a stable numerical basis that can be mathematically combined across any two disparate scoring systems, regardless of whether they are semantic scores, keyword scores, or even proprietary scores. This ensures that the intelligence from both the vibe checker and the accountant is treated equally based on perceived importance. Let's look at the Reciprocal Rank Fusion formula, RRF deconstructed, the fusion algorithm. The RRF score is the summation of the reciprocal ranks for a document across all lists. The formula shows the RRF score equals the summation of 1 divided by the constant k plus the rank. The rank component is the document's position in an agent's list, such as number 1, number 2, or number 3. Sigma, the summation symbol, means we add the resulting values from each list together to produce a final, unified RRF score. The crucial element here is the constant k, which is typically set to 60. This k acts as a smoothing factor. By adding 60 to the rank, we effectively dampen the influence of the absolute top few ranks. This prevents a rank 1 score from completely dominating the ranking and ensures that the fusion is more balanced, allowing documents that rank moderately high on both lists to still compete effectively with documents ranked first on only one list. This mechanism is key to achieving a robust, reliable result. To illustrate the power of RRF, we run a case file debrief, tracking Python. The Ghost's dense intel provides document A as rank 1, document B as rank 2, and document C as rank 3. The archivist's sparse intel ranks document C as 1, document A as 2, and document D as 3. When we calculate the fused RRF ranking, document A is highly ranked on both lists, ranking 1 for Ghost and 2 for the archivist. Its RRF score is calculated as 1 divided by 60 plus 1, plus 1 divided by 60 plus 2, totaling 0.032. Document C, which was ranked highest by the archivist, scores 1 divided by 60 plus 3, plus 1 divided by 60 plus 1, totaling 0.031. Although document C was rank 1 in one list, document A wins because of its consistent, high ranking across both conceptual and keyword analyses. Document B, which was only found by one agent, receives a much lower score. The conclusion is that document A wins. Its corroborated status gives it the highest priority, demonstrating how RRF correctly prioritizes shared relevance. We can best understand the outcome of this protocol by visualizing the fusion, the zipper effect. On the left, we have the dense results from the Ghost. On the right, the sparse results from the archivist. The middle column is the fused RRF ranking. Notice how documents that appear high on both lists, such as document A, are propelled to the very top of the unified ranking. Similarly, document E, which was ranked 4th by the Ghost but 1st by the archivist, jumps significantly in the fused list. Conversely, documents found exclusively by only one operative, like document D or document G, are relegated lower in the final ranking. The fundamental principle of RRF is boosting documents corroborated by both operatives. A target that is highly relevant semantically and contains the exact keywords rockets to the top of the unified list. This combined approach ensures we capture targets hiding in plain sight or targets that are obscured by complex language, leading to a much more accurate and complete retrieval set. The real success of this protocol is seen in the fact that mission success, a robust shortlist, is acquired regardless of the query type. RRF is designed to be self-adjusting. Consider scenario 1, the fuzzy query. A user asks, "How do I fix the screen?" This is highly conceptual, and the Ghost's dense results, which understand the meaning of fix and screen, dominate the RRF score, leading to mission success. In scenario 2, the specific query, a user asks, "Error 404." This is an exact identifier. The archivist's sparse results dominate the RRF score, accurately retrieving the precise document. Again, mission success. Finally, scenario 3, the hybrid query, a user asks, "How do I fix error 404 on the screen?" This utilizes both conceptual and specific terms. This is where RRF is critical. Agreed upon documents that scored well in both conceptual and specific searches rise to the top, synthesizing the best of both worlds. The result is a robust, highly reliable retrieval system that guarantees success across the full spectrum of user input. Although the RRF protocol successfully provided a robust ranking, we now face the next challenge: from shortlist to final target. Our retrieval phase was successful, generating a shortlist of 25 to 50 potentially relevant document chunks, which we call our top K results. However, sending all 50 documents to the final decision maker, the large language model, is inefficient, extremely expensive, and risks confusion. The LLM has finite context window capacity, and feeding it marginally relevant information dilutes its ability to make the best decision. We must now distill this list to the absolute best 3 to 5 chunks of actionable intel. We need to eliminate noise and false positives that may have slipped into the top ranks. This funneling process requires a final, meticulous layer of analysis, confirming the highest value results before they proceed to the next stage of generation. We execute this final distillation step through final verification, deploying the Overwatch analyst. The final step is called re-ranking. The shortlist of 25 to 50 documents is passed to a powerful, specialized asset, the re-ranker, which utilizes a cross-encoder model. This is fundamentally different from the initial retrieval. This is not another field search. The re-ranker performs a deep, comparative analysis of the top candidates already identified. Unlike the initial retrieval models, which score documents independently, the cross-encoder looks at the query and the document simultaneously, producing a highly accurate, deep relevance score. The Overwatch analyst reads the full text of the top results, and Ray orders them for maximum accuracy, ensuring only the 3 to 5 chunks containing the absolute highest value intelligence proceed to the LLM. This final verification minimizes cost, maximizes precision, and guarantees the highest quality output. We are now prepared for the next phase. Coming up, Chapter 7 details the Ray ranker's final cut.